Next presentation from Manan SURI from the Indian Institute of Technology at Delhi.
Hi, morning. So this is a collaborative work with the Meta Reality Labs and our group at IIT Delhi. In our group, we mainly focus on various use cases of emerging memory technology, non-volatile memory devices, how they can be used for various optimization use cases and so on. In this specific study, what we have done is we have evaluated NVM for some of the benefits that NVM can bring in workloads related to XR or extended reality. Now, the key essence of this work is we try to exploit the normally off computing due to the nature of workload, basically non-volatile inference accelerators. We try to analyze the memory and power budgets for the hybrid architectures through design technology, co-optimization, and design space exploration. So an entire modeling chain was set up for different XR-specific workloads, all the way from the workload till different device technologies. We also made some estimates for projecting at different technology nodes, different types of emerging NVM devices like MRAM, STT, SOT, VGSOT, and so on. The metrics that come from the benchmark, various headset devices need to fulfill a lot of performance criteria for different applications, whether it is the refresh rate or the power budget and so on. Some of these values from across different vendors are listed over here. So these are the broad constraints that one needs to look for in these cases. So the first task here was to get hold of the most relevant workloads. We chose two workloads here. One was the eye segmentation based on the open EDS dataset, most relevant in the XR context, to be precise. The other one was the hand detection, the first-person hand action benchmarking. And we started off with first getting the networks functional, training them on these datasets. The one for the open EDS was the UNet with the backbone of MobileNet V2, and for the hand detection, it was the DetNet or inspired from the Megatrack study. So, these are just some glimpses of the samples. Now, you can also see the network topologies over here. So after getting the networks working, the next step was to quantize them for the edge. And specifically with respect to the hand use case, one had to look at three different aspects: getting the hand label, the center radius, the center coordinates, and the radius of the hand application, hand detection application. So just to give you an idea of the size of the networks that we are talking about, these are the typical parameter sizes that we ended up in this case. So these are some results which show comparable inference accuracy even after quantization, going from float 32 to int 8 and beyond. So change in the distribution of the weight matrices when you quantize. So once the quantized networks were realized, the next step was to lay out the hardware benchmarking pipeline for evaluating different types of use cases or accelerators. So we took three architectures here to get a starting baseline. The first one was a typical CPU architecture. The next two were systolic or systolic-like, one inspired from the Iris design and the other from Simba. The need for choosing these two was to, the Iris being more, relatively more local memory fabric compared to Simba, which has more shared memory fabric across the PE blocks. And apart from the base architectures in terms of these accelerators, the next aspects that we looked into was playing with the the PE fabric, the number of computational blocks, the optimization of the memory buffers, whether it is the input-output weight buffer or the global buffer, and also the memory bit widths. So one of the key challenge here was that different tools, different estimation tools, going along with different type of architecture. So we tried to build a uniform framework where we were using several different tools like time loop, accelergy, NVSIM, cacti for various aspects. So if you go through the paper, you can also access the framework which came about it. So once these three baseline architectures and their different flavors were established, the next step was to see that in a purely CMOS implementation, how does the scaling play out? And that analysis was taken from 45 to 7, 40 to 7 nanometers, and at least as a ballpark, there was at least 4x saving between the extreme nodes, but then again, the returns are diminishing as we go around 7. So a key point to note here is that this is EDP and not just energy. So if you were to compare the CPU, obviously there are more gains in the energy, whereas you get significant latency gain with the two systolic accelerators here. So this was all till the point we were dealing with complete CMOS. Now once this is set up and this is functional, the next step is to start injecting the NVM or the non-volatile memory, how it can start helping with further gains. So what this chart shows is, the typical, let's say, flow of how the operation would happen at the any headset workload. It would start with frame acquisition. Moving from frame acquisition, there will be a wake-up stage for the accelerator, and then the inference, and finally, before the next request comes, you get the opportunity to power gate your accelerator. So now the idea or the concept here is that in an SRAM based, all SRAM based variant, you would have to put it on standby or some sort of hold state, whereas if you were to inject NVM, the power gating aspect of the the workflow, you can literally power it off and save the leakage energy or the leakage dissipation or the need to write back into the SRAM when you so this is basically the point which is being exploited here. Now, if you do a more detailed split of the memory-centric AI inference operation, you can have the read inputs, reading of the weights, the compute, which is the output of the inference, as well as the writing operations. Now, in the traditional case, these are the players that you would have at each stages. You would have DRAM or SRAM for the read stage, and again DRAM or SRAM for the reading of the weights, then for the registers all SRAM, and for the write stage also SRAM. Now just in all the variants that we studied, we completely got rid of the DRAM. We did all SRAM based realizations, and when you start introducing NVM, there are two flavors which we proposed here. The first one being more conservative, where the MRAM or different MRAMs are introduced only for the weight memory matrix, and the other one where the MRAM is used for almost all steps, just except the intermediate compute, where you need really high speed SRAM. So we term them as the P0, which is the conservative replacement of SRAM, and the P1, which is more aggressive replacement of SRAM with all MRAM kind of variants. So now what emerges from this? The obvious benefit is the area the area savings that you get compared to the the SRAM only macro versus the MRAM macros, and both for Simba-like or Iris kind of architecture, significant area savings for the P0 and the P1 variants were observed. Now, when we come to the energy, it gets really interesting here, because what is happening is, for some of these new NVM devices, the energy behavior for the reads and the writes, it's not very symmetric, and different stacks are optimized for different goals. So it's not very intuitive that if you will see gain consistently across all nodes So there are some intricacies. For example, at the 28 flavor of the P0 variant, we could see significant drop even in the CPU with MRAM realization, about 50% drop in terms of absolute trends, about 80% drop in the Iris, and 70% for the Simba, and so on. Now, what is also important to realize here is that on one hand, the NVM itself, it's not very symmetric. The nature of the workload also becomes, can be either read dominant or write dominant for different places. So these charts, what you're seeing here, they go into a more deeper dive to analyze both the split of the memory operations, the compute, as well as the impact of the NVM specific characteristics. So at least for the 7 nanometer, what we found is that both P0, P1 variant, it suffers on the energy front compared to the SRAM only variant. And the main reason for that is the 7 nanometer MRAM macro, which was considered here, is essentially read dominant. Sorry, the XR application is read dominant, but the MRAM macro which was used here for the analysis was write dominant, because write energy is a more obvious problem. So the within the MRAM, so that is what most studies are out there on. And similarly, the memory read energy and is greater than the memory write energy in the P0 variant. So there are intricate trends, and one can, it all depends exactly which kind of technology stack is chosen with respect to the application. So here you see the CPU one is more compute dominated, and the systolic ones, because owing to the parallel nature, are more memory read dominated. Now, one realization over here was the choice of metrics. So a more refined metric to evaluate the benefit of introducing NVM into these applications is something that we define as the IPS, or the inferences per second over the entire op time. So traditionally, you would look into just the FPS or the frame, the inference dissipation for processing each frame. But because of the fact that we are really exploiting the hold time or the erratic time after which the next inference request comes, it's essential to have a metric which captures this phase as well. So that's why we define the IPS as the inferences per second over the entire op time. And we feel this is a more relevant metric for these kind of substitutions for the XR workloads. And the reason being, again, from uses, from real use, what it was seen is that the workload is indeed quite asymmetric, infrequent, and sometimes can also be considered as an dominantly off kind of application, where you get enough opportunity to turn off your accelerators and bring them back again. That is the essence where you start exploiting the non-volatility. So let's say we set a target IPS of 10 for the hand detection use case. So meaning that even in a non-symmetric case, one would need at least 10 inferences or 10 frames to be processed a second for the hand detection use case, and 0.1 for the eye segmentation use case. So use only during the initial gaze tracking or the gaze estimation, or if there has to be an authentication for the user wearing the headset. So these are the chosen minimum IPS specs. So once we have defined the IPS, what we can do is what you see on these charts is the total memory power, the weight memory power versus the IPS. And these, the black squares are the one which show the SRAM dissipation trend, whereas all these squares are all these symbols are the different flavors of the MRAM, whether it is STT, SOT, or very aggressive VG SOT. So the point to note here is a crossover point. So as the IPS demand of your application increases, or the IPS frequency of the application increases, it starts eating into the idle time. And when it starts eating into the idle time, that's essentially when you cannot really power gate it or exploit the non-volatility. That's why you have a crossover point over here. Now, if you just, what I just mentioned is for the hand application, it was 10. So the sweet spot here is between 10 and this 60 crossover point. So depending on the actual XR workload, whatever points you get in between the minimum IPS and the the crossover point, that is the play space where you start gaining with the NVM substitution. So for both the applications, we were able to find some range for the optimization and the benefits. So yeah, so this is the point where you have to stay below the IPS crossover point. That's where the energy saving would come. And just to summarize, both for Simba-like and Iris-like architectures, if you go for a 64x64 PE fabric, the gains that you would see in DetNet with a IPS min of 10, the memory power savings or the energy savings would be at least always above 24%. So decent gain. And for the Iris, what we found is it was lower it was negative in the case of EDSNet. That's also due to the more memory intensive nature of the workload or the network. So yeah, so clear power saving even with the write optimized MRAM, and if this was to substitute it with the read optimized one, these gains could improve further. So to conclude, detailed study on two XR AI workloads, hand detection and eye segmentation, design exploration of mapping workloads on CPU and various systolic flavors, node scaling, getting a modeling framework all the way from the application till the quantification or the benchmarking, and two variants, P0 and P1 for with that I'd like to end. Any questions? Or